Okay, so what I'm going to do now is I'm going to teach you chapter 4. So I'm going to go to chapter 4, which is a bit difficult, chapter 4. Okay, so you may find a little bit difficult to understand chapter 4. So I will go slowly and make sure that you understand the question. So chapter 4 ni, they got pro and cons. Dia punya cons is when I explain about the equation, you'll be a bit confused because to derive the equation, it is not that easy. However, bear in mind that you will not be tested on the derivation of the equation, but rather you will be tested on how you use the equation to solve the question. Okay, so that's the pro and cons. You don't have to memorize. However, you have to really understand why there are so many equations and which equation to fit to what kind of situation, right? So that's the challenge, right? So I go one by one. Why do I say that you got so many equation? Okay, so chapter 4, we're going to start to do reactor design. Okay, we are going to find the volume for the flow reactor, or we will find the reaction time for the batch reactor, or sometimes, as I told you, maybe I give you the volume, you are expected to find the other parts of the equation depending lah on the question that is given to you. So it depends. So sometimes maybe question tu bagi volume, so cari benda yang lain, ataupun cari benda lain, cari volume, and so on and so forth. And for chapter 4, we are still discussing isothermal reactor design. Means dalam kita punya reactor tu tak ada perubahan suhu yet. Later we go to chapter 6, we will discuss when you have changes in temperature. So at this moment, you don't have to worry about the changes of temperature. Okay, you just consider the reactor sizing, right? So why this chapter is difficult is because now you're combining the knowledge that you have already learned in chapter 1, chapter 2, chapter 3, and now you combine everything in chapter 4. So what do I mean by that? All right, in chapter number 1, you have learned the design equation, right? We have learned the design equation for reaction time in a batch reactor. So equals to Na naught integrating from 0 to x because it's from 0 conversion to the desired conversion dx per minus RAV. That one kita dah belajar dalam reaction time for batch reactor. For PFR, we learn to find the volume. So volume PFR equals to FA naught, integrating from 0 to x dx per minus RA. We have seen it before, and subsequently volume CSTR. Kalau single reactor, FA naught X per minus RA. Kalau dia dah single reactor. Okay. Then in chapter 3, you have learned the rate law. Okay. You have learned kita nak cari rate law ni macam mana. So minus RA depends lah. First order ke, second order ke, first order with respect to A ke, first order with respect to B ke, so on and so forth. So kita akan ada rate law yang berlainan. So kamu perasan, equation design kita ada minus RA. Minus RA kita pula ditentukan oleh the nature of the reaction. Kalau reaction tu first order with respect to A, minus RA, KCA. If the reaction is second order with respect to A, minus RA, KCA squared. If the reaction is first order with respect to A, first order with respect to B. So minus RA equals to KCA, CB, so on and so forth. That's why we have different rate law. So kalau ada tindak balas berlainan, rate law berlainan, equation kita pun jadi dah berlainan. So now you understand second part why we have many equation. And third, to make it more complicated, kalau kamu perasan dalam rate law kita ada CA, ada CB. Kan? Kita namanya, kita kena express juga CA dan CB tu. Sebab kita nak CA and CB in the form of CA naught X. Kita dah tak dalam bentuk CA ataupun dalam bentuk CB. So tu yang menjadi masalahnya sebab depends on system pula. Kalau dia adalah batch system, okay, kalau liquid atau gas, dia tak apa. Concentration dia adalah masih sama. Kita express CA equals to CA naught in bracket 1 minus X. Kejap saya guna pen. Okay, so let's say kalau kita, kalau dia adalah batch liquid or gas, CA masih sama CA naught in bracket 1 minus X dan CB kalau B adalah reactant sama dengan CA naught in bracket theta B minus B per AX. So kalau dia adalah batch, you don't have to worry about that. It's the same regardless of the phase. But the problem will be kalau dia adalah flow reactor, CSTR, PFR, sekarang concentration dia dah express berlainan. Kalau dia adalah liquid phase, flow reactor, concentration dia, if you realize Ca and Cb is similar to batch. So liquid flow sama dengan batch, yang hanya berbeza adalah gas flow. So kalau gas flow, kalau kamu nampak saya ajar chapter 3 kan, this is what we learn in chapter 3. So chapter 3 kita ajar kalau the gas flow reactor, because inlet outlet volumetric flow rate tak sama. Okay, and in this case, at this equation, kita assume isothermal isobaric. So P naught per P tu tak ada, T per T naught pun tak ada lagi. Maka we can write Ca equals to Ca naught 1 minus X, 1 plus epsilon X, which you have done in chapter 3. And Cb equals to Ca naught in bracket. Kejap ni macam susah sikit saya nak guna. Dengan laser pointer. Cb pula equals to Ca naught in bracket theta B minus B per Ax per 1 plus epsilon X. So beza dia adalah kalau liquid atau gas, kita tak ada pembawah tu. Tetapi kalau dia adalah gas, dia ada pembawah yang 1 plus epsilon X. Bear in mind patutnya ada P naught per P, T per T naught. Tapi sebab kita masih assume constant pressure, constant temperature, maka P naught per P, T per T naught tu tak ada. So part ni kalau kamu a bit confused, go to chapter 3 notes, part yang express concentration tu, you will understand better. So now you understand? I have 3 information yang saya kena combine sebab dalam law saya ada minus RA. Dalam minus RA saya ada CA. CA saya pula kena express dalam bentuk Ca0 dan X di mana it can be different for liquid phase and gas phase. So that's what we're going to do in chapter 4. We're going to combine all this information into one. So let me go first into batch reactor. Okay, kita tengok sekarang. Kita nak cuba express the design equation. Okay, bear in mind, you will not be tested on the derivation. You'll be tested on how to use the equation. But you have to understand lah macam mana equation tu derive, or else you wouldn't know to use which one at which situation. Okay, so for batch reactor, why do we need to do that? Because laboratory scale batch reaction is required in the scaling up of laboratory experiment to pilot plant operation or full-scale production. So as I told you previously, biasanya kalau dia adalah tindak balas yang baru and kita nak memahami dia punya conversion, dia punya reaction time, we always will use batch reactor dahulu. So bila kita dah faham the reaction itself, then only we will go upgrade to flow reactors. Okay, so that's why we need to know batch reactor. Then next, data from batch reactor can be used to determine the reaction time to achieve a conversion, or in some cases the reaction rate constant. So what we do is usually kita nak guna design equation batch reactor ni untuk cari reaction time. Ataupun sometimes kita boleh suruh cari X ataupun suruh cari K. So depends. What do we know and what do we want to find? Okay, and this information kemudian akan digunakan untuk kita design batch flow reactor, right? Okay, so let me go to first part. Okay, why do we have so many equations? Sebab rate law kita ada 3 jenis rate law yang berlainan. Okay, to be honest, there are more rate law, tetapi I will just cover the basic one. So minus RA equals to KCA, minus RA equals to KCA square, minus RA equals to KCA CB. So first order reaction and second order reaction, which is second order with respect to A, or first order with respect to A and first order with respect to B. Concentration pula, okay, liquid atau gas kita express sama. Ca equals to Ca0 1 minus S, Cb equals to Ca0 in bracket theta B minus B per A X. So that's the easiest part. Dia adalah masih equation concentration yang sama. So now let me express the very first equation. Again, kamu tak payah bimbang sangat pasal derivation because the most important for you is to actually understand how to use the equation. So derivation tu taklah begitu penting untuk kamu sebab equation tu will be provided to you, but of course it's important that you understand how this equation is being used. Right, so let's say now for batch reactor. Okay. Right. Okay, so now let me express for batch reactor first order reaction. Bear in mind that this is applicable for both gas and liquid phase reaction. Okay, so but this is reaction di mana adalah first order with respect to A. Okay, so how do we derive the equation? So first of all, kita akan selesa start dengan design equation batch reactor kita. Okay, so design equation batch reactor kita, originally, it was reaction time for batch reactor equals to Na integrating 0x dx per minus RAV volume. Okay, now when you're integrating something towards X and volume, okay, is not you will not be you will not be integrating towards your volume. So you can take out your volume from the integration part of your equation. Sorry, so when you take out, the volume now will come out, you become an A naught per volume. Okay, because batch reactor constant volume. So you can write the outlet volume reactor as equal to inlet volume reactor. So I got NA naught at the top, V naught at the bottom. So NA naught per V naught equals to CA naught. So the integration part is still the same, 0x dx per minus RA. So you can see I transform my equation based on the understanding that I will not be integrating towards my reactor volume. So I take out, and then because my batch reactor volume inlet outlet to sama, so I can make it into V naught. So NA naught per V naught, I get CA naught. So now my design equation for my batch reactor, T batch equals to integrating CA naught, integrating 0 to X dx per minus RA. So now you see, second, minus RA tu kita kena ganti dengan case pertama when if my rate law minus RA equals to KCA. Okay, first order with respect to A. Third, sebab CA saya tu saya kena jadikan dalam bentuk CA naught dan X. So you may ask, kenapa kita kena buat macam tu? Sebab kita nak integrate towards X. We are integrating towards X. But my minus RA is not yet in the form of X. That's why I have to change it. I have to elucidate CA in the form of CA naught and X. So I get CA, which I've learned in chapter 3, sama dengan CA naught in bracket 1 minus X. So sekarang CA saya dah ada dalam bentuk X. So how do I combine 1, 2, 3? Okay, so we can see from here. So reaction time for batch reactor equals to CA naught 0x dx per minus RA. Kita ganti minus RA dengan rate law yang kita nak buat sekarang, KCA. Tetapi again, CA kita tak boleh integrate terhadap X. Kita mesti perkenalkan X. But we know KCA sama dengan CA naught in bracket 1 minus X. So you see here now. So you see now become KCA naught 1 minus X. Okay, so in this case, when this happen, what we do is K dan CA naught takkan berubah dengan X ataupun it will not be integrated with X. Apa-apa yang variables yang tak ada kaitan dengan X, kita bawa keluar daripada part integration tu. So I can take out my K CA naught, I take out. So previously I have a CA naught outside, so CA naught ikut divide by K CA naught yang saya bawa keluar. So integration saya tinggal 0x dx per 1 minus x. Okay, so at this part, what you do is, alright, so you can see here, CA naught saya boleh batal, saya tinggal dengan 1 per K. So part luar ni saya dah settle lah, saya tinggal 1 per K. What about this integration part? Okay, so for this integration part, technically you have to integrate. Okay, so the solution for this integration is already given to us. Penyelesaian dia kalau you nak integrate from 0 to x dx per 1 minus x as this, the solution is ln in bracket 1 per 1 minus x. Tu solution integration dia. So solution integration tu kita combine dengan 1 per k yang tadi. So part luar tu kita tak kacau, dia masih kekal. Integration part tu kita dah kamirkan, kita dapat penyelesaian dia. Ln in bracket 1 per 1 minus x. So we combine this both and we derive the final equation. So maksudnya batch reactor time equals to 1 per K ln in bracket 1 per 1 minus X tutup bracket. So meaning for reaction, batch reactor, first order with respect to A and both liquid and gas, the time is given as 1 per K ln in bracket 1 per 1 minus X. Maksudnya, katakan reaction kamu ni kena memenuhi ketiga-tiga syarat ni. Batch reactor, first order with respect to A dan dia adalah liquid atau gas. Kalau salah satu dia tak penuhi, this equation is not valid. Okay, so this reaction maksudnya equation ni, if you're given K, you're given X, you can find reaction time. Ataupun mungkin saya beri kamu reaction time, saya bagi kamu K, saya suruh kamu cari X. Atau I can give you K, I can give you reaction time, I can give you X, you have to find K. Either way, okay, so equation dia ada 3 variable. Kalau saya beri kamu 2 variable, kamu dah boleh cari variable yang ketiga depending on the question. Okay, so this is for first order. We go to, kalau dia adalah reaction of which it is second order with respect to E. Apa pula berlaku? Tadi KCA, sekarang adalah minus RE dia KCA power of 2, second order with respect to A. So, dia punya design equation ni masih sama. Okay, T batch equals to CA naught integrating 0x dx per minus RE. Design equation takkan berubah. Kenapa kita ada equation yang lain? Sebab sekarang rate law kita dah berbeza. Katakan tidak balas kamu sekarang, minus RA equals to KCA power of 2. And similar to the previous case, CA tu kita kena jadikan dalam bentuk CA naught dan X. Terutamanya sebabnya kita kena ada X tu. Sebab kita kena integrate towards X. So CA equals to CA naught in bracket 1 minus X. So I combine 1, I combine 2, I combine 3. Okay, so T batch equals to CA naught integrating 0x dx per minus RA. Minus RA, I now replace with KCA power of 2. Tadi KCA sebab rate law dia first order with respect to A. Now rate law dia second order with respect to A, KCA power of 2. Then CA power of 2, saya kena gantilah. Kalau CA sama dengan CA naught in bracket 1 minus X. Kalau saya ada CA power of 2 become equals to CA naught power of 2 in bracket 1 minus X power of 2 as well. Okay, so dah jadi dalam bentuk yang ketiga ni. So same concept, K dengan CA naught square ni dia takkan dikamikan terhadap X. Dia tak ada kaitan dengan X. So you take out from the integration part. Sebab dia takkan dikamikan terhadap X, you take out from the integration part. So dia akan menjadi CA naught per K CA naught square. So kita hanya boleh cancel satu CA naught. So it can become 1 per K CA naught. So bahagian luar integration tu saya dah settle. Dia akan menjadi 1 per K CA naught. But what about our integration part? So now we are integrating 0 to X dx per 1 minus X bracket power of 2. Okay, again kalau saya bertanya, anybody wondering why 0 to X? Because this is single reactor, we're integrating towards from 0 to your final conversion. Okay, so for this integration part, dah ada penyelesaiannya, pengamirannya, the solution is given as X per 1 minus X. So integration tu penyelesaian telah diberi, maka we just copy the integration solution and we combine with the front part previously. So that's why menjadi 1 per K CA naught in bracket X per 1 minus X. So this is to find reaction time in a batch reactor. If you have a reaction of which it is second order with respect to E. Any other rate law, any other reactor, this equation is no longer valid. So same case, if you're given K, CA naught, dan X, you can find reaction time. Or if you're given reaction time, CA naught, X, you can find K. Or you're given reaction time, you're given X, you're given K, you can find CA naught, so on and so forth. So again, sini ada 4 parameter. If I give you 3 parameter, you can find the 4th parameter already. So depends on the question, right? So we are done for second order with respect to A. And we go to the very last one, the reaction of which it is first order with respect to A and first order with respect to B. Sebelum ni hanya ada A kan, tapi sekarang kita melibatkan A dan B. So we see how to do it, right? Okay. The desired equation is still the same. T bash equals to CA naught, integrating 0x dx per minus RA. Okay, then reaction dia sekarang minus RA KCA CB. Now kita kena express CA dan CB. So part CA ni dah normal lah kan. CA equals to CA naught in bracket 1 minus X. What about CB? So kita dah belajar chapter 3. If CB is a reactant, CB is expressed as equals to CA naught in bracket theta B minus B per A X. Okay, so theta B ni adalah initial amount of B over A. B per A ni adalah stoichiometric coefficient. Okay, now, because of the limitation of this integral formulation, okay, maka B per A yang di hadapan X ini harus menjadi 1. Kalau tak nanti kita nak selesaikan pengamiran tu, kita tak boleh selesai sebab formulation dia ambil kira yang B per A ni adalah 1. But you don't worry, if it comes up in the test of final exam, I will make sure the B per A is 1. Maksudnya tindak balas 1A, 1B lah. Supaya kamu tak akan confuse kenapa B per A tu jadi 1. Okay, so now it become CB equals to CA naught in bracket theta B minus X. Sebab B per A itu adalah 1 disebabkan the limitation of the integral formula. Okay, now I'll explain why, right? Okay, so kita combine lah kan. So reaction time equals to CA naught integrating 0 to X dx per minus RA. Minus RA I'll replace with KCA CB. Okay, then K masih ada. CA equals to CA naught 1 minus X. CB equals to CA naught, another CA naught in bracket theta B minus X. So dah ada. Okay, so again, any variables yang tak ada kaitan dengan X, kita bawa keluar. Kurungan kita tak kacau. Sebab nanti kita dah ada direct formulation dia. So kita tak kacau kurungan yang ada X. Kita just bawa keluar any other variables yang tak ada kaitan. So K kita bawa keluar, CA naught we take out, another CA naught we take out. We take out tu maksudnya keluar daripada part integration tu sahaja. So dia akan menjadi CA naught yang asal ni divide by K CA naught square. So I got 1 CA naught at the top, 1 CA naught at the bottom. I can cancel. I'm left with 1 CA naught. So dia menjadi 1 per K CA naught. Bahagian belakang sekarang integration menjadi 0 to X dx per dalam bracket 1 minus X theta B minus X. Itu part pengamiran dia. So again, untuk pengamiran especially macam ni, kita dah ada solution dia. So this is the easiest part for you. You don't have to worry about the solution. It's already provided to you. So it's given as 1 per theta B minus 1 ln in bracket theta B minus X per theta B bracket lagi 1 minus X big bracket. Okay, so that solution I copy and I combine with previously the front one which was 1 per K CA naught. So part pengamiran tu kamu tak payah bimbang. Solution dia dah ada. Kita petik masuk saja dan kita combine dengan bahagian yang luar tadi yang kita dah ada. So you get T bash equals to 1 per K CA naught in bracket 1 per theta B minus 1 ln theta B minus X per theta B in bracket again 1 minus X. So this one is slightly harder. The equation is becoming longer kan sebab rate law dia dah berbeza. So again, this equation is only valid if you have batch reactor, liquid or gas, and rate law dia specifically minus RA equals to KCA CB. First order with respect to A, first order with respect to B. Any other rate law, equation ni dah tak valid. So similarly, if you will be asked to find, let's say, batch the reaction time, we will give you K, CA naught, X, theta B. Mungkin you will be asked to find K, but we give you the other parameter. So dia ada banyak variable. Kesemua variable tu akan tinggal satu yang kamu kena cari, yang selebihnya akan diberi information untuk mencarinya, baru kita boleh solve. Right? So in a nutshell, this is the 3 equation that I've already taught you, of which now you understand how to find the reaction time for first order reaction time for second order, of which minus RA equals to KCA square, or when minus RA equals to KCA CB. Alright. Okay, so let us do one question. Okay, so for example, the question says, given a liquid phase reaction takes place in a batch reactor, reaction is first order with respect to A, first order with respect to B. So kamu terus kena tahu rate law dia. Okay, so minus RA equals to KCACB. So kamu kena tahulah kalau rate law KCACB, batch reactor, equation mana yang kamu kena guna. So that part you have to be very careful to know which equation you will use. Right, so dia kata, reaction dia A tambah B produce C. 60 mol percent inert reactant B, balance is A. Okay, so diberi kamu YB not 0.6, hence YA not 0.4. So YB not 0.6, YA not 0.4, you get your theta B ready kan? Dah tahu YB not, tahu YA not, boleh cari theta B. Given reaction rate constant K 0.1, initial concentration of A 12, CA not 12, K 0.1, CA not 12, X 0.3. Sebab dia kata 30% converted. Okay, so kita tahu X, kita tahu K, kita tahu CA not. Kita tahu YB not, YA not, theta P. Dia nak kita cari reaction time, T. Okay, so nak cari reaction time, alright. So from the information, kamu terus tahu formula mana. So kamu kena tengoklah formula mana yang kamu boleh gunakan. So you must remember at this moment, baru 3 equation, senanglah. Tetapi when you learn so many more equation later on, you have to really know which one is for which situation. Okay, so since I only have to find reaction time, saya boleh cari theta B, saya ada YB not, YA not, saya boleh cari theta B, saya ada K, saya ada CA not, saya ada X. I can find my reaction time easily, and the answer is 1.9 second. Meaning to say, for this reaction, to achieve 30% conversion in a batch reactor, they just need 1.9 second. So that's all for batch reactor, and next we will go to continuous stir tank reactor, right? CR. So previously I already explained about how to derive the equation for batch reactor. Now we will go for CSTR. So the other pro and cons here, CSTR is slightly easier sebab CSTR punya design equation tak ada integration. It's just a very basic linear equation. But the challenge is that now CSTR is a flow reactor. Therefore, you have to bear in mind whether it's a gas or liquid phase reaction. Sebab kalau gas phase, equation dia dah berlainan. Kan ingat sebab kita express concentration untuk gas phase dah lain dengan liquid phase. Okay, at this moment, kita consider lagi tak ada perubahan tekanan, tak ada perubahan suhu. That's why the concentration is expressed as Ca equals to Ca naught in bracket 1 minus X per 1 plus epsilon X. Tu beza dia. Kalau liquid, just Ca naught in bracket 1 minus X. Kalau dia gas, ada pembawa 1 plus epsilon X. Same for the B as well. Pengatasnya adalah sama. Pembawa dia saja. Kalau ada gas, kita akan tambah 1 plus epsilon X. And then, because of this concentration berlainan dan juga rate law dia mungkin boleh jadi berlainan. So I just covered the 3 main common rate law. Minus RA equals to KCA, minus RA equals to KCA square, minus RA equals to KCA CB, the common ones. Okay, so disebabkan expression concentration dah berlainan, expression design equation dia pun akan berlainan sudah. So you will have 6 different equation for CSTR. Tadi batch hanya 3 sebab liquid dengan gas sama equation dia. Sebab tu kita ada 3 rate law berlainan, 3 equation. CSTR kita ada 3 rate law yang berlainan tetapi kita ada concentration yang dah berlainan. So 2 kali concentration, 2 concentration berlainan, 3 rate law yang berbeza. So jadi 6 equation yang kita kena belajar. So let me go to the very first one. I cover first liquid phase sebab liquid phase ni senang sikit saya cover. Okay, so untuk liquid phase reaction, initially the volume of CSTR is given as a design equation dia Fa naught X per minus RA. Single reactor CSTR, design equation dia V CSTR sama dengan Fa naught X per minus RA. Now I'm doing for the first rate law of which minus RA equals to KCA. Okay, first order with respect to A. Third, kita express concentration sekali lagi. So Ca akan menjadi Ca naught in bracket 1 minus X sebab this is liquid phase reaction. Okay, saya buat dulu liquid phase reaction. So again, kita combine 1, 2, and 3. So the volume CSTR equals to Fa naught X per minus RA saya dah menjadi KCA. Then saya replace CA dengan CA0 1 minus X. So saya dapat dah equation yang warna merah tu. Volume CSTR equals to FA0 X over K CA0 in bracket 1 minus X. So done the first red equation to find the volume. Okay, volume CSTR. However, dessert equation ni, alright, maksudnya katakan kamu nak cari volume, kamu diberi FA0, kamu diberi X, kamu diberi K, kamu diberi CA0, kamu boleh cari volume. So let's see pula, kamu tak diberi FA0 dan CA0. Okay, how do we find the volume? Okay, so you remember that FA0 per CA0 is actually equals to epsilon naught. Kalau kamu ingat perkaitan dia, FA0 per CA0 sama dengan epsilon naught. So maksudnya saya juga boleh mencari volume of your CSTR which will equals to epsilon naught X per K in bracket 1 minus X, the green color. Meaning, if let's say you're given epsilon naught K X, you can find the volume. If you are given FA0, X, K, CA0, you can also find volume. So if you ask me which one to use, depends on the information you are provided. Okay, kalau diberi epsilon naught, boleh juga cari. Given FA0, CA0, you also can find the volume. Right? Then next one, let's say we want to find space-time. So remember we learned in chapter 2, not only we can find volume, we can also find space-time. Sebab space-time is given as volume per volumetric flow rate. Remember, space-time tau is equal to volume per volumetric flow rate. So you realize on my left-hand side, I have volume. On my right-hand side, I have the epsilon naught. So if I move my epsilon naught from right to left, you become division. So volume divide by epsilon naught. So this one become tau CSTR. So on the right hand side, tinggal saja X, tinggallah yang bawah K1 minus X. So now I already express as well the space-time for your CSTR, which is equal to X per K 1 minus X. Okay, so again, all these three equations, syarat dia adalah your reaction must be first CSTR, second, it must be a first order with respect to A, and third, it must be liquid phase reaction. If your reaction does not fulfill all three, then you cannot use this equation. So equation ni very specific. Kamu kena memenuhi this syarat, then only you can use the equation. Bear in mind that I only provide you the equation of the red color ones. So saya beri kamu the original version, volume CSTR sama dengan FA0 X per KCA0 in bracket 1 minus X. Yang lain tu, you have to learn to derive yourself. So, kamu kena fahamlah berkaitan FA0, CA0. Kamu kena faham berkaitan space-time. Then only you can solve this equation. So, similarly, tengok apa equation diberi, apa yang kamu kena cari. Okay, done. I go to the next one. Okay, we will talk about something new, that a number which we call as Dam-Collar number. So what is this Dam-Collar number? All right. First thing first, Dam-Collar number, we use it the alphabet DA to signify Dam-Collar number. Second, Dam-Collar number ni ada specific application. Dia hanya untuk specific two types of scenario. First one is when you use a CSTR liquid phase first order reaction, which I just taught you, or when you have CSTR liquid second order reaction of which minus RA equals to KCA power of 2. So dia hanya boleh guna kalau liquid CSTR dengan rate law yang satu minus RA equals to KCA. The second one when the rate law is minus RA equals to KCA power of 2. Any other rate law, any other reactor, any other phase, you cannot use this Dam-Collar number. Okay. Apa tu Dam-Collar number? Alright. So if you see from this equation, originally kita tahu yang space-time for CSTR is given as X per K in bracket 1 minus X. Yang tadi sebelum ni saya yang derive, yang purple color tu, okay, this equation. Now, I will move my K from the right to the left. So, daripada pembawah dia akan jadi pengatas, tu akan become tau K. space-time multiply with K, and this is what we call as Dam Collar number, dan ini bersamaan dengan X per 1 minus S. So, apa pentingnya Dam Collar number ni? A Dam Collar number is a dimensionless number, nombor yang tak berunit, tak berdimension, that can tell you a quick estimation the degree of conversion in your CSTR. Maksudnya, even before kamu run eksperimen ni, kamu kira dulu nilai Dam Collar number ni, kamu dah boleh estimate sama ada the conversion will be a high conversion or low conversion. So, how to calculate dia? Dam Collar number equals to space-time darab dengan K. So, you know space-time tu sama dengan volume per inlet volumetric flow rate. So, means kamu tahu volume reactor, you know your inlet volumetric flow rate, you can get your tau, you multiply with your K, reaction rate constant. So, as I taught you before, untuk reaction, normally kita dah tahu nilai K tu, okay? Dan kita dah establish nilai K ni berdasarkan tindak balas kamu. So, you can get your tau K value. So, you get tau K value, you will calculate your Dam Collar number. So, if your Dam Collar number, you get 0.1 or less than 0.1, it tells you that your reaction will most likely give you very low conversion of 10% and below. So, means sebelum kamu run eksperimen tu, kamu kira Dam Collar number. Kalau kamu dapat 0.1 dan ke bawah, kamu dah boleh tahu that conversion dia adalah lebih kurang daripada 10%. Jadi rendah lah. And if you calculate your Dam Collar number, it gives you 10 or more than 10, it tells you that your conversion will most likely be more than 90%, which is high lah, which most likely tell you that you can get good conversion, high conversion. So you may wonder, why do we need to know this? Okay, so you can see your Dam Collar number ni berkaitan dengan space-time dan K. So katakan nilai Dam Collar number kamu adalah rendah, of course we must increase it, because or else if you run the reaction, you know that you will get low conversion. So how do we do it? Okay, we know that tau space-time is volume per volumetric flow rate. Okay, of course volume saya tak boleh buat apa-apa. The reactor volume I cannot do much unless you change to a bigger reactor, sebab Dam Collar number dengan volume will be equal, satu naik, satu lagi akan menaikkan, dia goes up, dia berkadar langsung. Okay, sorry, the word is directly correlated, which if I want to increase Dam Collar number, I have to increase the reactor volume. But let's say you cannot increase reactor volume, you must remember space-time equals to volume per volumetric flow rate. So meaning, dia ada berkadar songsang, reciprocal. If I want to increase my Dam Collar number, I have to reduce my volumetric flow rate. So means saya slowkan volumetric flow rate saya. Or value of K. So kalau value of K macam mana pula? Sebab nak Dam Collar kena tinggi, K pun kena tinggi. How do you increase K? Remember I told you, K increases with temperature. So if I can increase temperature, my K value will increase, my Dam Collar number will increase as well. So that's why Dam Collar number is very precious. It gives you a value of estimation of how your reactor will function and what you can do if let's say you predict that your conversion may be low, right? So that's how and why we learn Dam Collar number, right? So now let me go to the next one. Let me derive the equation for second order CSTR, of which this is now liquid phase second order reaction. Okay, so kita derive one by one. So this is the equation dia, volume CSTR, volume CSTR sama dengan FA0 X per minus RA. Now rate law dia minus RA equals to KCA power of 2 second order with respect to A. Okay, then we express CA again, this is liquid phase. Therefore, CA equals to CA0 1 minus X. So again, we combine 1, 2, and 3. So minus RA, we combine, we replace with KCA power of 2 sebab rate law kita adalah KCA power of 2. Then CA, kalau CA sama dengan CA0 in bracket 1 minus X, CA power of 2 equals to CA0 power of 2 in bracket 1 minus X pun power of 2. So you will get the equation in the red color form. So volume CSTR for liquid second phase CSTR, second order CSTR is equal to FA0 X per KCA0 in bracket per KCA naught square in bracket 1 minus X power of 2 close bracket. This red color font equation is provided to you, meaning you can find your volume if you know FA naught, X, K, CA naught. Ataupun mungkin kamu disuruh cari K kalau diberi volume FA naught, X, CA naught. You can be asked to find K and vice versa. Okay, then remember, I have another version. If let's say you are not given your FA naught, but instead you are given epsilon naught. So equation ni ada format yang berlainan bergantung kepada soalan. So if you are given epsilon naught, you can still find the volume because they have one FA naught at the top and one CA naught at the bottom. So you know if I divide FA naught per CA naught, you will get epsilon naught, right? Divide epsilon naught with you divide the FA naught per CA naught, you get an epsilon. So you can replace now if the equation become volume CSTR equals to epsilon naught X per K CA naught in bracket 1 minus X power of 2. You just managed to cancel one CA naught. That's why the other CA naught is still at the bottom. And then next, we can also find space-time. So remember, we can find dia ada format yang berlainan. So format pertama bila saya ada FA naught, CA naught. Format kedua untuk mencari kalau saya ada epsilon naught. Both is for volume reactor. And the third version is to find space-time. So sama konsep lah. If I got epsilon naught on the right, I bring it to the left, it become division. So volume per volumetric flow rate equals to space-time. So bahagian kanan dia hanya tinggal X per KCA naught in bracket 1 minus X power of 2. So now you already express the design equation for CSTR liquid phase where the reaction is second order with respect to E. Right. Now we will go to the question of Dam column number again. So again, kita boleh cari Dam column number untuk case second order reaction. Tetapi formula dia lain sikit dah. Okay, apa maksud dia? So from just now space-time of second order reaction equals to X per K CA naught in bracket 1 minus X tutup bracket power of 2. Okay, so again apa saya buat? I will move my K and CA naught from right to left. So it become multiplication. So Dam column number sama dengan space-time times with K times with CA naught. So this is my Dam column number. So again, I will calculate my Dam column number just by knowing your space-time. Because your space-time is volume per inlet volumetric flow rate. Darab dengan nilai K. Of course, you know value of K depends on your reaction. And CA naught is initial concentration that you prepare of your reactant E. So you calculate same concept. If you get anything 0.1 or less, it tells you that your conversion will be less than 10%, very small conversion. Or if it's more than 10, that means that your conversion will be at more than 90% conversion, so high conversion. So again, if your Dam column number is small, you already know what you need to do. Okay, means you can already predict that your conversion will be low. There are things that you can control the system. So first, that I discussed previously, either you change to a bigger reactor volume or you reduce your volumetric flow rate, or you increase temperature because the K increase with temperature, or you increase the concentration of E. Sekarang itu benda baru yang kamu boleh manipulate. You can manipulate the initial concentration of E. So maybe previously you use 2 mole per liter, maybe you change to 10 mole per liter, you increase. Because when my CA not increase, my Dam column number increase, most likely then your conversion will increase as well. So you see, how powerful this Dam column number, of which it can help you to predict your reaction and to improve on the reaction even before it occurs. Alright, so done for second order reaction. So now remember that Dam column number hanya boleh dikira untuk two situation where the rate law is first order with respect to A, and the second order reaction which is second minus RA equals to KCA power of 2. Any other rate law, we cannot find the Dam column number. Okay, so next one, I will go to the very last one for liquid phase second order reaction. So liquid phase second order reaction says that, alright, kita akan buat first one by one lah kan. So volume CSTR equals to FA naught X per minus RA. So rate law dia minus RA equals to KCACB. So we try the next rate law minus RA equals to KCACB. And then we express again the concentration. So CA sama dengan CA naught in bracket 1 minus X. CB equals to CA naught in bracket theta B minus B per AX. Both are expressed like this because they are in liquid phase reaction. Then you combine lah 1, 2, and 3. So minus RA in our design equation is now replaced with KCACB. Then kita replace. First CA akan menjadi CA naught 1 minus X. CB, another CA naught in bracket theta B minus B per AX. Because I got 2 CA naught, that's why dia akan menjadi CA naught multiplied with CA naught jadi CA naught square. That's why you have your CA naught square, then you have your key, and then you have the bracket. Okay, so again, this formula is to find volume of CSTR if the reaction is second order with respect, first order with respect to A and first order with respect to B, liquid phase CSTR. If your reaction does not fulfill all these three, this equation cannot be used. Then the same equation can be transformed in the form of epsilon X. If let's say instead of given Fa naught, you're given epsilon naught, you can still find. Okay, bear in mind saya hanya beri the main equation. Yang derivation dia, yang selebihnya kamu kena cari sendiri, kamu kena derive sendiri. Once you have already gotten the second version of the equation, so now you have to then, similarly, we have to find the space-time. So space-time sama, you know that space-time is equal to volume per epsilon naught. So you move the epsilon naught from the right to left, so it become a division, it become bottom. So you will get your tau, your space-time for CSTR equals to X per KCA naught in bracket 1 minus X in bracket theta B minus B per AX. So similar to the other one, you have different version of the equation depending on what information is given and what you want to find. Are you finding volume? Are you finding space-time? So on and so forth. Right, so we have already done on liquid phase, of which I already covered all the reaction order. Now we will go to liquid gas phase. So gas phase ni a little bit difficult where the equation becomes a bit more complicated solely because the equation that expressed differently for concentration, because now your concentration instead of Ca equals to Ca naught in bracket 1 minus X, now it becomes Ca equals to Ca naught in bracket 1 minus X tutup bracket 1 plus epsilon X. That's why the equation becomes complicated because now it becomes the concentration expressed differently. But let us do again for the three different rate law. So the design equation, volume CSTR equals to Fa naught X per minus Ra. So I do for the first rate law, minus Ra equals to KCA, first order with respect to A. Okay, then kita dapat concentration, kita express sekarang sama dengan Ca naught in bracket 1 minus X per 1 plus epsilon X. So we combine 1, 2, 3. So we get volume CSTR equals to Fa naught X per KCA, because our rate law is KCA. K masih tinggal, tapi CA tu dah menjadi CA naught in bracket 1 minus X per 1 plus epsilon X. So you remember mathematics, when I have 3 layers of variables, A per B per C, yang C tu akan naik ke atas, dia akan naik to the top. So A per B per C become AC per B. So now you get the volume of CSTR equals to Fa naught X in bracket 1 plus epsilon X per KCA naught in bracket 1 minus X. So tengok yang tadi 1 plus epsilon X yang kat bawah dan naik ke atas. Okay, so this first version is what that you're going to be provided in your test or your final exam. Okay, maknanya kalau you have Fa naught, you have X, you have epsilon, you got K, you got CA naught, you can find the volume of CSTR and vice versa. Tak semestinya sentiasa kamu disuruh cari concentration, dicari volume. Sometimes maybe I give you volume, you have to find other variables. Tapi yang penting kena faham apa yang ada dan apa yang kena cari. Okay, then the green one, again second version, kalau we don't have Fa naught but we are given epsilon naught. Kita pun boleh cari sebab from the original equation, I have FA naught at the top, I have 1 CA naught at the bottom. FA naught divided by CA naught is epsilon naught. So katakan kamu diberi FA naught, CA naught, kamu boleh guna equation pertama. Tapi katakan kamu tak diberi, but you're given epsilon naught, you can still find because you can transform the equation. So now become epsilon naught K 1 plus epsilon x bracket per K1 minus x bracket. So again, nak cari volume, you can use the second version depending on the information. And the third version is to find space time. So again, nak cari space time, just move the epsilon naught from right to left. So you get your space time. So bahagian kanan tu, yang lain semua akan kekal lah. So let's say you're asked to find space time or you're given information on space time, you can use the third equation. Right? Okay, so similarly, we are going to do for second order reaction. So sekarang tadi kalau minus RA equals to KCA. Sekarang kita buat kalau minus RA equals to KCA power of 2. Okay, so same concept. I will replace again. Okay, so I will replace volume CSTR equals to FA naught per minus RA. Minus RA sama dengan KCA power 2, power of 2. Then CA, kalau CA equals to CA naught, 1 minus X per 1 plus epsilon X. Kalau CA power of 2 becomes CA naught power of 2, 1 minus X power of 2, 1 plus epsilon X per power of 2, as shown in this side. So again, the third layer will goes to the top. So it becomes volume CSTR equals to FA naught X, 1 plus epsilon X power of 2 per KCA naught square, 1 minus X power of 2. So don't forget, bila kamu square, kesemua terms tu kena square sekali. Okay, so again, first version, if I know FA naught, I know CA naught. The green version, if I know epsilon naught, so I just divide 1 FA naught ke atas dengan 1 CA naught di bawah, kamu dapat epsilon naught. So you get the green version of the equation. And then the third version to find space time. So now I hope you understand kenapa kita ada banyak equation. First of all, sebab rate law berlainan. Then concentration pun can be different, depends on the phase. Rasa the equation akan berubah. And then depend juga information diberi. Kalau diberi FA naught, CA naught, saya guna yang red version. You are given epsilon naught, I use the green version. If you are asked to find space time, yeah, you use the last version as well. Okay, and the last one for the CSTR gas phase is a reaction of which first order with respect to A, first order with respect to B. So minus RA equals to KCACB. So you can realize by now, so just cover 3 main rate laws. So you can see even 3 main rate laws, but you got a lot of equation, right? So that's why you just have the idea how we covered for the usual rate laws. Okay, so in this question, dia jadi makin susah sebab rate law dia dah susah sebab ada CB kan. So CA kita tahu masih sama dengan CA naught minus X per 1 plus epsilon X. CB sama dengan CA naught in bracket theta B minus B per AX. Kalau liquid dia berhenti di sini, tapi dia adalah gas per 1 plus epsilon X with the reminder that kita assume constant pressure, constant temperature pada masa kini. Okay, alright, then you combine again lah. You combine rate law, design equation with the concentration of A, concentration of B. So you can see now, it become slightly complicated sebab kita dah ada concentration A, concentration B. Okay, ultimately, you get the final equation in the red color one or in the green color one for epsilon. Kalau red color is FA naught, CA naught. Green color kalau diberi epsilon naught. Dan the purple one if you are given in terms of space time. Okay, so again, equations provided to you are the red color ones. So you really need to know how the equation changes depending on the question given to you. Okay, right. So this is how I summarize back every equation that I have already explained to you in the case of CSTR. So you can see there are many equations, right? Just that what I gave you is in the red color font. The remainder is something that you have to understand and derive yourself. But it's not that hard sebab kamu dah tahu FA naught dengan CA naught berkaitannya dengan epsilon naught. Kamu pun faham apa tu space time. Kamu tahu space time diberi sama dengan volume per epsilon naught. So kamu tahu, kamu ubah persamaan dia, you can really get 4 to find for the space-time as well. Okay, all right, so that's all for the case of CSTR.